Sort of did power analysis last week, and my overall approach being to look at three different approaches and powering just for t-test and chi-squared. So there are a couple of things I left out that I want to cover today regarding power analysis. One question that comes up often is you can have unequal numbers in the groups that you're comparing. What is the consequence of that? Do you gain anything, or do you not gain anything? And so I want to explore that today first. And people may recall in my first lecture, I talked about case control and exposure control studies, where good studies typically would have multiple controls for each subject. So for each case, they may have 5 controls or 3 controls or whatever. And if it's an exposure match study, for each person with the exposure could be smoking, or the exposure could be breastfeeding, whatever. And they would have multiple people who are not exposed to that intervention. And so the question here is, is there a benefit to that? So that's what I want to talk about a little bit here. And I'm sorry, I don't have the URL up there. So I would like you to be in your browser, go to biomath.net/power and go to chi-squared, comparing two proportions, and then work on the right side. And so this is a project that actually came from one of the pediatric residents who did our rotation a couple of years ago. So she had a project where she had tissue samples from 32 cases of I forget what the condition was. Might have been a cancer, and her lab found a novel biomarker that was in 16 of the 32 case tissue samples. And so the question was for her to design a case control study. She wanted to get control samples, which of course there are plenty of control samples available, to see if this 50% prevalence of the biomarker in the case tissues was significant or not, and was it different from controls. And so it's a large cohort, as I mentioned, so you can have as many controls as you want. So, so the question here is, how does the power change, and how much does it change if you can increase the number of controls? And her interest, by the way, as I mentioned in the slide, was that apparently the biomarker, at least to start with, was very expensive to measure. So she was trying to minimize her expense as well. And as I said in the slide here, if you increase the number of unexposed controls for a given number of exposed subjects, you have a similar situation. So the question is, what happens if you alter the control to case ratio? So what I would like you to do is to start from the second panel here and put in 32. So 32 is the number of cases my resident had, and 0.5, 50% was the prevalence of the biomarker. If you type 32 and 0.5 and you click on result, you should see this. The 0.15, that is, you can detect a proportion less than 0.15. What that means is, if you have 32 cases and 32 controls, then if the control prevalence of this biomarker is less than 15%, then there is power to show significance. And so now, this is something that we haven't looked at till now. So there is a group 2 to group 1 ratio down at the bottom of that. So if you change that 1 to 2, what that means is you have 2 controls per case. and what's the effect of that. So you put 2 here and you go back and click result. And so you now have, this shows up as 0.18. So what that means now is that if you have 2 controls per case, then you have somewhat greater power. That is, you can find significance not only if the control prevalence is below 15%, but even now, if the control prevalence is as much as 18%, you can find significance. So that's what you have gained by doubling the controls. If now we say, okay, let's suppose we have 4 controls per case. So you go back and you change this 2 to 4. And when you do that, and you click on result, you now are up to 20%. So that means that if you had only 1 control per case, you could only find significance if it is below 15%. But if it is 4 controls per case, you're able to find significance if it is less than 20%. And that's what you have gained by going from 1 control per case to 4 controls per case. So this is the point of the increasing the number of controls per case. So I hope people appreciate that, this is a common problem, that in many situations, like in my president's case, the number of cases is fixed. You can't increase the number of cases, but the controls can be increased. And so you you say, how much benefit can I draw from doing that? So now let's see what happens if you go from 4 controls to 8 controls per case. So that is, from going from 1 to 4, there was a reasonably, I would say, significant improvement in power. It went from 15% as the threshold to 20%. But what you see is that if you go from 4 to 8, it goes from 0.2 to 0.21. So that, unfortunately, is not much. And this is the point that I want to make, that when you increase controls per case, it does help, but it's diminishing returns. That is, each additional set of controls you add, you don't get as much benefit. So when you go from 1 to 2 to 4, you went from 15 to 18% to 20%. But if you increase it further, you're up to 21%. And it'll keep going up, creeping up very slowly as the number of controls increases a lot. And finally, just as a point of comparison, I would like you to change the 32 here to 64 and change this back to 1. That is, you go back to 1 control per case, see what happens. So what you see here is that when you double the number of cases with the same number of 1-to-1 case control ratio, you in fact have much greater power. Instead of 0.15, 15%, you're up now to 25%. So, that's a huge increase in power, which is not achieved anywhere near that by going from 1-to-1 to 2-to-1, 4-to-1, 8-to-1. And in fact, you can show theoretically that if you had infinite controls, you may even want to try that. If you try like 1,000 controls per case, you will come close to 0.25. That is, that what you can achieve by increasing the number of controls, it will never be better than doubling your cases. So I trust people see this. And the remaining thing in power analysis that I want to cover is equivalence and non-inferiority. And this is a little bit tricky, and please feel free to interrupt me because I may not even be explaining it so well. We talked about it at the beginning of power analysis last week, that I was saying that if you design your study to detect the least significant difference of clinical interest, then um, a negative study there can be interpreted as showing equivalence of a kind. And so I want to expand on that here in a more formal way. And so one approach to equivalence study would be you just take the second approach, and you say, I'm going to consider the treatments equivalent if they differ by less than something. So you say if they differ by, if you're looking at some lipid level, you say if they're different, like the example I did last week of switching to a diet in a public health setting, you say, well, if it doesn't lower cholesterol by even 5 milligrams per deciliter, I'm not going to be interested. I'm going to consider that equivalent, not not better. And so you say, so you design the study for that 5 milligram per deciliter. And so that would be one way to do equivalence. So to state it slightly differently, if a study designed to detect the smallest difference of clinical interest is negative, one can conclude with 80% confidence, if the calculation is done at 80% power, that the difference, if any, is not of clinical interest. So this is the, I'm just re-showing what I did last week. So we found in our study that the standard deviation of the cholesterol change was about 14 milligram per deciliter. And we said, well, you want to promote this mono-enriched diet, but if it doesn't drop it even by 5 milligrams per deciliter, I'm going to consider it not superior, equivalent. So if the diet effect in a study with 125 subjects, this is what the power analysis gave. If the diet effect with 125 in each group is non-significant, then we can conclude that any difference, even if it exists, will be under 5 milligram and not of clinical interest. So this is sort of accepting the null hypothesis. I know people may have been, drilled into people that you can never accept the null hypothesis, but this is sort of accepting the null hypothesis. We're not saying that that the mono diet and the standard American diet are absolutely equivalent with respect to cholesterol change. All we're saying is that if there is an effect, that effect is smaller than what I consider to be of interest. And therefore, they are equivalent, and so that's the null hypothesis. So this is a null hypothesis with a slight modification. That is not that they are identical, but they are within some margin. So, for instance, we did another power analysis last week where the study is, doomed to fail study, which explored the power of prayer in preventing complications post-cabbage. Then they said a significant thing would be 55% versus 45%. And so we power the study for that, and we end up that they need about 500 subjects. So if the prayer effect in a study with 520 in each group is non-significant, which is what happened, they didn't find significance, we can conclude that any difference, even if it exists, will be under 10% and hence not of clinical interest. So that is sort of accepting the null hypothesis. But the problem here is that people may well say, even a 5% effect, coronary artery bypass graft is a big procedure, and any improvement would be meaningful. So even a 5% effect is of clinical interest because prayer has no side effects and is inexpensive. This negative study would be of much value. So that means if you are designing an equivalent study, there has to be consensus on what constitutes equivalence and what constitutes non-equivalence. So these people said, well, 10% would be, less than 10% would be equivalent. But somebody else can come along and say, no, 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 even 5% is good enough for me. So then the study has to be different, obviously. Okay, so now let's switch to non-inferiority, which is sort of like equivalence, but slightly different. And so non-inferiority is quite important when you're coming up with a new procedure or a new drug. And so the question can be asked, is minimally invasive surgery non-inferior to standard of care open surgery? Right? That can be a question you ask. Oral bisphosphonates were standard of care. And then you had this new thing come along, which was annual infusion for people who couldn't tolerate the oral bisphosphonates. So you could say, is the annual infusion non-inferior? The goal is not to show that the annual infusion is better than oral bisphosphonates taken daily or weekly, but you just want to show that it is non-inferior. So how do you do those things? So, so what I would like you to do is to go back to another design and work with non-inferiority. So we're going back to the New England Journal study. So what we found there was step 1 had a drop of 15 milligram per deciliter, and the mono diet had a drop of 20 milligram per deciliter. And so we think that the mono diet is more appealing to people than the step 1 diet for the simple reason that it has a higher fat content. The mono diet has about 35% fat calories as fat, and whereas step 1 has only 30% of calories as fat. So we think that the mono-enriched diet may be preferred by people, more appealing. And so we just want to show non-inferiority of mono in relation to step 1. Now, based on our previous study, we think, in fact, the mono-enriched diet may lower cholesterol more than step 1 does. So this is what we're going to go through these steps here. And again, folks, this does get to be a little bit convoluted, perhaps in reasoning. And so just, stop me, or if you feel like it, tune out, because you could say, I'm not interested in this part of power analysis. So I would like you to do a different design with pick t-test, because this is what we're doing here. And so you see the interface is a little bit different now for non-inferiority. There are many things being displayed here. So I'm just going to explain these one by one. The reference mean is the mean that you're comparing the mono to. In this case, is step 1. So we know that in step 1, the mean drop was 15. And the test mean applies to the group that you're interested in showing is non-inferior, or the treatment you want to show is non-inferior. And so that is 20 milligram per deciliter. And of course, the standard deviation. So you put those numbers in, and then if you click on result, it'll tell you how many subjects you need to show non-inferiority. This says 125, which, remember, this is roughly what we had before. And when we said maybe the smallest difference of clinical interest is 5, you see, difference that exceeds 5. So we say that if, so then you get 125. But maybe you don't need to show this. This is where it gets to be a little tricky, and I may not be the best person to explain this, so bear with me. Suppose mono is better for other reasons, as I mentioned, that the fat content is makes it more appealing to subjects, to the general public. So you could say it would be considered non-inferior if the drop on mono was at least 13. Doesn't have to be better than 15, but doesn't have to be as good as 15, but at no more, at least 30. So if the drop should be at least 13, so now you see that the numbers are different here. When you didn't do anything here, it started off with the actual difference that was there between 15 and 20. But you can change that. You can change that 15 to 13 and say, I'm okay if my mono diet drops cholesterol by at least 30. I'm going to consider it non-inferior. You notice 13 is not as good as 15, obviously, but you can say for other reasons, mono is preferred. And so if it does it even 13 milligram per deciliter, I'm okay with it. So you put that in and you get a new number. So what this says is that 64 subjects in each group would be enough to show that the mono diet is no worse than 13, no worse than 2 below the 15. So that's what I apologize. This wording here is not exactly friendly, but I haven't come up with any better wording. If anybody has suggestions, I'm happy to listen. And then finally, you could even have a situation where the mono is not better than step one. It's the same, 15, 15, but you just want to show that it is no worse than 30. So you can do that as well. But of course, now you need a lot more subjects to show. That is, you want to show that it is not inferior when in fact you have the same, you expect the same response, and you need a lot of subjects. So just to contrast the three situations, the three things that I worked out today, if you have if you just start with what you think you know, 15 and 20 in the two groups, and you want to show it's non-inferior, you need 125. But if the non-inferiority can go down from 15 to 13, then you need fewer subjects. And if in fact you expect them to have the same drop, then you need a lot more subjects. So that's the story. So I'm done with power analysis now, but I do want to make sure that everybody has R and CU functions there. So that's what I want to make sure now. So this was the general summary of the things you had to do. Install R and RStudio and the 11 add-on packages, and then the R profile, which is done with that command download .file, and then install CU functions. And finally, for people who have Macs, this I didn't talk about in my setup. For people who have Macs, which I imagine many of you have Macs, it turns out to produce editable graphs. I'm going to show you how R can produce nice graphs. Whatever functions I'm going to teach you, there are graphs produced and they are decent quality, and you have some control over colors and so on. But you may want to have additional control over the graphs you produce in R. And you may want to change some text or add some text and so on, beyond what flexibility CU functions offer you. So for that, you want to be able to create editable graphs. That is, graphs that are not just images, but that you can actually open in PowerPoint and add things to it. Now, it turns out that's a trivial thing to do in Windows. For whatever reason, I'm always willing to blame Apple for monopolistic practices. The R people are able to, they have an option when you export a graph from R. If you're in a Windows machine, you can choose what is called a meta file, and then it will create uh, a copy that you can paste into PowerPoint, which is editable. I'm going to show all this. You know, we won't get to it till next week, but this is what is going to happen. But if you have a Mac, that option is not there now. Maybe they'll bring that option available sometime, or maybe there's something fundamentally impossible to do on a Mac in Apple systems for that. So then you have to do uh, a somewhat more convoluted process of having another version, another type of word processing program called OpenOffice. It's a free open source program, but that is the way you have to take your graph and make it into something that PowerPoint, the usual Microsoft PowerPoint can deal with. So you may have no interest in it. For instance, I have no interest in it. Uh, for one thing, I have a Windows machine, even though it died, and um, and but I'm actually working right now with a couple of my students um, who on a paper, and they've produced graphs in R, and now they want to put that into the manuscript, and they need to make some edits on the graphs. They have Macs, so they have to be able to do this thing. Um, so that's the point of the open office. Okay, and so so um, so so this is the first step after you have RStudio. So the reason I'm saying it is that this takes time, even when it works. The 11 packages, can take a few minutes. So is anyone else that was unable to install the 11 add-ons? And maybe an unfair question. Really, it'll become obvious only when you get to CU functions. So I trust everyone did this with no difficulty. The R profile file, that should be I mean, just copy and paste this into your RStudio, and it should have worked. And so this is where the problems will come to light. That is, the reason they'll come to light is not so much there are CU functions create problems, but that CU functions package tells R that it needs those 11 add-on packages. So if any of those packages is not installed in full, this will fail. And for it to, how do you know that it has succeeded? So it has succeeded. I'm going to assume that things have worked, and just want to get to people feeling that they have succeeded in installing, and go through and relaunch RStudio a couple of times and so on, and it will finally end saying star done. And if the installation ends with star done, that means that your installation is successful, that you're ready to go. Except maybe OpenOffice for Mac users who want editable graphs. And so now, just as a final test, assuming you all did this before today already, you should quit RStudio after you install CU functions, and then launch it, and you should see this message from my now retired colleague, Steve Holleran, saying R profile. The date is not important. It might say 2021 now. And if you see this, then you're done. Final test uh, for people who think they've got everything done, is that you launch RStudio. That is, after you install CU functions, you exit RStudio and you launch RStudio. Um, and if you type just $CU read, this is just asking for some help message for one of our functions, one of the CU functions. You should see something on the lower right of your RStudio window, and just a little thing saying, what CU read does. This is how help messages work in R. You type some function name, and then it'll tell you how to activate that function, use that function. So, so this is the big question here. Is anyone else not able to get this to work? Do I assume that everyone else is okay with it? So I'm sorry, I forgot what AN3093's name should be. So you don't actually have to install RTools. It tells you to install RTools, but in my, I never installed RTools, and I think it's okay. But there's no harm in installing RTools. It gives you more power. If you say some general things about R now, so let me just say a couple of things now, which I will repeat next week. Just things to watch out for when you're using R. So you make any sort of typo, if you make any error when you're typing something into R, you don't get any particularly helpful message. And so, for instance, we have a function called CU table 1. The purpose is to produce the standard table 1 that you see in papers. But one of the students recently mistyped and just typed $CU table without the 1. And so when you do that, it just tells you no documentation for CU table, blah, blah, blah. You could try something. So it doesn't know that, you left out the 1. And another error that somebody else made was they forgot the question mark. They just typed CU table 1. What that does is it starts to actually display the entire source code for that function. So the syntax is very terse, and it's not interactive particularly. And so when you get an error, just look carefully at what you typed more than the error message that R produces, and see if you spot some typographical errors, and then try to fix that. So that would be the thing. And our functions, Steve and I worked on these functions, but the way R works, which is very nice, is that it's an open source thing. So when you install our functions, our package, you have access to all the source code that we wrote. So if at any point you type a name of our CU function without the question mark, it'll actually display the source code in your console. So that is one thing I wanted to say. And the other thing, so these are the functions I'm going to be teaching, 11 functions that I believe pretty much encompass what people would want to do with their own data. This is all I need to do with my data, I find. And then to help people run these functions, I have I have a crib sheet file which you will find in the Biomath.net resources as a way to have on the side if you have questions about how to invoke a function. And then so I'm not going to go into the details here. So for each function, it tells you how you would invoke it and what some of the options are and so on. And then there are many options. If you type, even now, if you type something like CU one way, CU one way, you'll see on the right, there are many options. Many of the options you won't use at all. So I'm not interested in, overwhelming you with all this stuff. Most of the time, you'll just have a couple of arguments and it'll do the analysis for you. But all the other things are for having more flexibility. And so just many possibilities. And finally, I have a tool now, a web tool, where you can actually, if you run this in your browser, you can pick a function and then say what you're trying to do, what sort of control you want, and so on. And it will actually, in an interactive way, it will construct the R command that you need to type, that you need to copy and paste to get your job done. So, I'm hoping that these things make it not that hard to use R. So so that's the goal there. And then this thing just gives an overview of our functions. So that is also linked in the resources thing. So I'm done with this one. So I think I'm going to stop here. I think we're doing well on time. That we can start our next week and make good progress. And